Yeah, and so today I want to talk about a few different things. I mainly want to talk about a bit of mean field control for Restless Bandits, and also put the name weakly coupled MDP in the title. But you'll see that I'm not really going to talk directly about weakly coupled MDP because this is sort of included in the rest. Anyway, feel free to interrupt me at any time. Yeah, I'll try to give some examples, to give simple ideas. So hope it should be understandable. Okay, so the basic, setting that I'm going to consider in some kind of a centralized mean field control problem, in which I have this sort of population of agents that I put on the right. N agents, they'll be like some small Markov chains, okay? Meaning that they'll have a discrete state and discrete actions. And so the idea is that the centralized controller will send a control to these agents. And I brought it this bold A, that it's a vector of control. So one control may be different to all agents. And then the agent will transition to some next state, will give you some reward, and you want to optimize this reward. And so the thing that makes this problem difficult is not that the agents are really dependent on each other, okay? We assume that they are all independent for a given action, but it's more like the actions makes the whole problem dependent, okay? Because you cannot send the same, any actions to anyone. And so the general idea that we are going to use is some mean field control idea, is that in a normal world, the size of the problem increases with n, okay, with the number of agents. But somehow, if you look at n equals infinity, the problem is simple. And so the idea is that we can solve the n infinity problem. And I will show you that for these kind of examples, these are really simple problems, like linear problems. But now the thing is that how to go back from this n infinity solution to the finite n problem. And so that's what I'm going to talk about. So how to use this infinite simple solution to my original problem, and also how efficient this is, meaning that in some cases, we know that this becomes optimal, but somehow we want to try to quantify how fast does this work. So I say this is like pretty generic, nothing special. And so the problem mainly I want to focus on today is Markovian bandits. So now I will slightly change the vocabulary and replace the agents by arms, okay? Because that's when you talk about bandits, people talk about arms. And so the idea is that each agent now is an arm. And so I have n arms in front of me. I will consider, so I said, a discrete time finite state space model. Discrete time is not necessarily the important thing here, but finite state space and action will, is sort of important. And again, for all my arms, they evolve independently if you fix the action. And here, the objective of the controller is to maximize some expected reward, that is the sum of the rewards for all agents. Okay, that's the T is not important, but it's important that it's really one reward per agent, and I just do the overall set. And so again, this problem like this is probably easy if I don't say what are the constraints on my actions. Okay. And so the constraint I'm gonna have here is that I have a C, which is some finite capacity. And what I have is that at all time, I should not, the sum of my action over all my arms should not be larger than C. And so what I'm going to focus here to make things simpler in this talk is the action is either 0 or 1. And 0, I mean, 1 means activate, okay? And 0 means not activate. And so if I go back to my multi-arm bandit thing, 1 would be I pull the arm, I choose this arm, and 0 means I don't pull the arm. Okay. And so here, C is just that, for instance, imagine that C is equal to 1. This is a standard multi-arm bandit setting. It's just that at each time, I should pull one of my n arms. I can pull any one. I should pull one of my n arms. And here, these are called Markovian bandits because each arm has a state. Okay, and so that's, I mean, this is the Markovian arms. Each arm has a state. And also, you see that we call this restless Markovian bandit because essentially when you pull an arm, the state evolves. But when you don't pull an arm, the state might evolve too. There is no restriction about what is the reward. There is reward when it's inactive. There is reward when it's active, etc. And as I said, that's probably, I'm going to stop talking about weakly coupled MDP for a while in this talk. But essentially, weakly coupled MDPs are almost the same models, but except that the actions are not just 0 and 1, can be somehow more general than that. And also, in general, the C here is not just a scalar constraint, but might be a vector constraint. And so you'll see that most of the techniques, not really all, but a lot of techniques that apply to Markovian bandit, they apply to weakly coupled MDPs. Yes.
So just a clarification with the notation, are you assuming all the arms are homogeneous or they can be independent?
So yeah, so there was a question that I will just repeat for maybe for the people abroad. So the question was, are the arms all homogeneous? And yes, at least for the purpose of the talk, all the arms will be homogeneous, which means that the transition matrix and reward do not depend on the arm identity. Somehow it could be lifted. It depends. But the thing is that what we are going to do is that now we are going to let n go to infinity. And for that, it's not mandatory, but it's simpler when everything is homogeneous. Okay, let me just start with 2 small examples. Okay, maybe not. Yeah, that's simplistic, but still two kind of different examples. And the first one is just an example of so it's called the applicant screening problem, and it's a finite horizon problem. And now the framing is as follows: that you have n applicants, so the applicants are essentially my arms, okay, and you have t rounds of interviews, and at each round of interview you can say, okay, I'm going to interview you, you, and you, and then you interview them one by one, and then there is a second round. You can interview other people, not necessarily the same. And at the end, you want to find the best candidates. And so the way this can be modeled is that with some Bayesian model, okay, where each candidate has some internal quality, okay, that I'll call it Pn here. And so if you use a Bayesian framework, Pn is somehow you can estimate Pn via the posterior distribution of what you think is the quality given the answers that this candidate provided to me, okay? And so for instance, a simple model is just that, okay, quality is between 0 and 1. When you interview a candidate, if it's a good candidate, it gives a 1 with priority Pn. So the higher Pn, the higher the chance that this person will give a good answer. And so the problem is just that you do this round of interviews, and at the end you want to select the best. And and so this problem is just is difficult because of these n candidates. It's a Markov decision process, but like the state is becomes pretty large, even for t small and not too. Second problem, which somehow is also a problem that we face in our everyday life, is what's called a job scheduling, what I call job scheduling problems. And the question is like, today you come to work, and it's like, what is the project on which you should work? So sometimes, you have things you have to do. Sometimes you have to choose your new project. And the idea is that if you have many tasks to do, some have deadlines, some are risky, they have high rewards, etc., etc. And so the question is, what should you work on? And so this is related to a topic that I'm quite familiar with, which is the queuing systems. And in that case, so imagine that you have different, these are the jobs on which we can work, and the server is you, and you want to decide, on which of these jobs should I devote my next half hour or hour, okay? So examples are, research project, but maybe some more like, scheduling problems in a data center or vehicle charging. And so there are lots of heuristics to control these problems. And for instance, there is this earliest deadline first that we all use, I think. Okay. You do the next thing that you have to do. But there are things like when for instance, the job sizes exactly, then somehow there are things like the shortest task first. Okay, that's what you should work on. But this assumes that you know exactly the duration of the tasks. And so when you don't know the duration of the task, the problem becomes more complicated. And the problem is related to my Markovian bandit problem, when in fact you don't know the duration of the task, but you just have some Markovian model of the tasks. Okay. Tasks have different states. You know the transition between the tasks, and you want to know who to schedule first. So all of these problems, I mean, maybe you can believe me on that. There are instances of Restless Bandits problem that they have been shown to be like P-space hard, which is a bit like harder than NP hard, so something that you can't really solve exactly. And the idea is that what we're going to try to do is how to find good heuristics for that. And as I said, what we want is to use this mean field ID, so the n infinity problem, to construct a policy in a sort of efficient manner, okay? And this is like solving the infinite problem will become really simple. Again, it's an LP. But also, what I will be trying to do here is to compute policies that are easy to implement. Okay, and by easy to implement, I mean that one of the questions will be like, if you take priority policies, and I explain later what it is, but if you take a priority policy, is this thing good enough, okay, to obtain some optimal policy? And so the question will be, are, for instance, priority policies close to optimal when n is large? And so, so that's essentially will be my first two questions, like when are priority rules asymptotically optimal, how to compute them, and in particular in all of these would be how fast do these policies become optimal as the system size grow. Okay, so we're not really, we're really saying like we have n finite, but we can solve the n infinity problem, and what does it say to us about the finite n problem? So that's sort of the agenda for today. I mean, some of these parts are shorter than others, so don't be too afraid. But I just first want to give you an idea of what is the n equals infinity problem in my case. And then I go to first the infinite horizon problem and talk about index policies. And I say some words about finite horizon problems at the end. Okay, so now just go back to my problem. I go back to my original problem where I have n agents, okay? Each agent are independent, but for this constraint on actions, okay? And the constraint on action is that I cannot activate more than the proportion alpha of arms. So I replace the constraint C by alpha times n, because now I'm going to scale n to infinity. And so I want to have the resource constraint also scale to infinity. And so the idea to relax this problem, okay, is just we're going to use a relaxation and just to say, now let's replace this for all t, I should have at most alpha n activation by the expected number of activation at time t should be smaller than alpha times n. Okay. And why is that interesting? This is because the problem just before was p-space complete. Now this problem is easy. This problem can be solved by an LP, linear program. And so just let me prove this claim so that we understand that this, I mean, it's a huge, maybe linear program, but in fact, it's a really simple one. The idea is that for now, okay, I'm focusing on this infinite horizon problem. There is no time here, and what I'm really be writing here is that XS will be the probability that a given arm is in state S, and YSA would be the probability that a given arm is in state S, and I take action A, again in steady state. And the idea is that if I look the Markov equation, like this is the Markov equation gives you the first constraint. The second equation is just that for a given state S, I should choose exactly one action. The last equation is just that the probability sums to 1. Okay, this is so these three ones are Markov equations, and this one is my relaxed constraint. Okay. That says that on average, I should activate alpha and fraction alpha. And so, okay, I don't want necessarily you to understand all this equation, but just say that, okay, this is an LP. It's therefore really simple to study, I mean, to solve. And the idea is that, okay, here I added just a layer of complexity that this thing is in red, just to say, okay, the side before was for infinite horizon. This one is for finite horizon. And the only changes are in red. Oh, okay. Here is the change that is not in red. Essentially, this is the same thing, but you add t, okay, and it works exactly the same. So now the idea is that, okay, this L infinity problem, you can solve it easily with a computer, and also obtain sometimes some nice properties of this solution. Now the thing is that, okay, now I can solve the infinity problem, but how to apply this to my finite problem? Now the first thing, just to realize that I wrote this V here. The V here would be the value function. And the idea is that because I have a relaxation, okay, the value function of my system N will be, of course, smaller than the value of my relaxation. Okay, I'm trying to maximize reward, so if I have fewer constraints, it's easier. But now, so the thing is that my original problem was I want to activate at most alpha or times n, but and here the expectation should be smaller than alpha. And so what's the difficulty to apply the thing on the right to the thing on the left is that my LP gives me a solution, I mean, one trajectory, but my stochastic system will never be exactly in X star, okay? And the idea is go, so X star, Y star would be the deterministic trajectory. And the thing is that when I apply stochastic transition, I will jump away, okay? And so the question is that because I jump away, you see that my Y star has a constraint that I mean I need to choose one action per state. Yeah. Maybe it's not that important if I write it, but okay. So at least in general, it's not possible to choose yn, so which would be the control for my stochastic system is exactly equal to y star.
Would you like to comment on the fact that these are sample, on the left-hand side, I've got a sample path constraint because the A's will be random sample path. In the limit problem, it's converted into a mean constraint, but in principle, you could actually preserve the sample path constraint on the right-hand side as well, couldn't you? I mean, it's harder, much harder, of course, because it's sample path, but there's sort of like there are two relaxations here, or two to facilitate the answer. One you go to infinity, fine, and you go to expectations, differently.
So I agree that I'm sort of cheating a bit here, which is that I mean what I'm hiding is that I'm saying, okay, this is the n equals infinity problem, but in fact, not really, because this thing that I have on the left, on the right, is just a relaxation, and you can apply it for n equals 4. Thank you. So this thing, in fact, it's not necessarily the infinite problem. It's just a finite problem where I have a relaxed constraint. And so what is hidden here, and I guess I'll come to it, is that, in fact, when n goes to infinity, this problem indeed converges to this one. Okay. But it's true that this problem is not really the infinite problem. It's just a problem where I have relaxed this constraint.
Right. So two right-hand side with an expectation, when also one could preserve the sample path.
But yeah, maybe I mean I should just write it here. Just maybe I guess it would be easier. But the idea is that for my relaxed problem, I have this thing that xa should be equal to sum over a of ysa. This is just I take one action per arm, and now the thing is that because so here now xn would be the fraction of items that are xn fraction of items that are in a given state S, okay, for the n system. And the thing is that this xns is not equal to my x star s. And so obviously I won't be able to choose yn exactly the same. But the question is how to do it. And so again, what I'm going to try to talk here is about two sort of complementary problems. One is the infinite horizon problem. And in fact, what I'm just going to go through a bit is that when you look at this infinite horizon problem, somehow this has maybe almost be solved by what is called what are called index policies. Okay, at least this relaxation directly leads to index policies, and we know that they are like asymptotically optimal in many. I mean, under some conditions that I will explain again. And so here I just, in addition, I'm going to present this result. And in addition, I want to present two of the results that we've been working on very recently. And first was about the rate of convergence, and the second one is about the computation of these index policies. And the second thing is about the finite horizon problem, and where, in fact, you can also define some index policies here that some people name this LP index. And in particular here somehow, I mean, here index policies are asymptotically optimal under some technical conditions, but in practice, these conditions are widely satisfied. Whereas for finite horizon, they are not, I mean, they are satisfied for many problems, but say not as many as here. Okay, and again, in fact, we can almost obtain the same results of exponential convergence. It's really similar to the previous case. Okay, so let me go back to the start with the infinite reason problem. So again, I'm looking at what I call this infinity problem, and in fact, as you said, what we did for this problem is that we replaced the sample path constraint by just a probability constraint, and in fact, it turns out that this problem with this constraint is called constraint MDP. Okay. There is a literature about constraint MDP. And so, in particular, MDPs are linear problems. So that's why the problem that I showed before is a linear problem. And in fact, this constraint here is linear. So that's why constraining MDPs are also linear problems. And that's why they have been studied, because they are easy to solve. And now the idea is that if you have a problem with a constraint, the one natural thing to do is to use some Lagrangian relaxation, which would be that here I replace this exact, this relax constant, but I relax again, if you want, this constraint of probability that I activate alpha by just, I put a cost lambda to choose the action A, the action 1. Okay. And this is just to say, this is just that I have sum of an equal alpha, and I just do lambda sum of an minus alpha. And so just why I'm saying that I'm using this, if I write it like this, you might say, but this would work also for the sample path and not just for the relaxed constraint. And the reason why it's not true is that if I want this to work for the sample path, then I need lambda to be adapted to the filtration, whereas here what I'm saying, just lambda is a real, is a scalar. So that's why here lambda is for the relaxed problem, and because I'm doing everything for the expectation. And in fact, it's because I'm just this function. And so now, okay, the idea is that because everything is linear, in general, there exists a lambda such that the value, the control for this problem is the control for the optimal one here. And the idea now is that if we can compute this lambda, then we are done. And now that's where index policies that I will define later are interesting. Because now the idea is to just reverse the thing a bit, is that to say, okay, now let's look at the lambda penalized problem. So the MDP where I have a penalty lambda. And now this graph is just to say this is the optimal policy as a function of lambda. And when I say optimal policy, that here I have two actions. Remember, action 1 or action 0. One is activate. And so the idea is that when lambda is minus infinity, you get plus infinity when you activate. So of course you activate everyone. When lambda is plus infinity, if you activate, you get penalized minus infinity, so you don't activate. So that's why here it's white, here it's blue. And the things that looks reasonable is that the set of optimal policies would look like this, meaning that there exists somehow a value here for each state. After which it's optimal not to activate if lambda is too large, and it's optimal to activate below that. So if the graph is really like this, then in fact we obtain the Whittle indices and we obtain Whittle index policies. And what are Whittle indices here? is just that you focus on each state, for instance, state 1, and there exists a unique lambda, called lambda 1, such that it's optimal to activate for this state if lambda is below lambda 1, and it's optimal to not activate the state for lambda larger than lambda 1. You do that for all the states. And what you obtain is the index of the state, okay? And here you see that the index for the state 3 is larger than the index for the state 1, larger than state 4, state 2, which means that you should activate first this state 3, then state 1, then state 4, then state 2. And what is really the, I guess, the really beautiful idea of this index policies is that here there is no alpha. Remember that remember that I had an alpha in my constraint. Okay. So yeah, I was just saying, I think that now the nice thing about the index policy is that it doesn't depend on alpha. And so what is, I think, really important about this is that what you obtain here is that it's not just a priority rule, but it's also that now if you have lots of heterogeneous now agents, all the agents are different, you can still compute indices for all the agents independently, again, and combine them together, and you obtain just more indices. But the complexity of the policy that you obtain at the end is still the same. It's just that you activate the agent that have the largest, that are in the states that have the largest index. Okay. Now, okay, as I said, this definition was a bit not completely formal because intuitively, when lambda is minus infinity, everything is blue, plus infinity, everything is white, meaning that probably there exists a place where you go from blue to white. Okay. Now, in fact, in practice, this is not always true. Okay, and when this is true, we say that the arm is indexable. Okay, when there exists a unique penalty lambda. Okay, going from blue to white. And I would say that not everyone agrees if this is most of the time like true with priority 1 or not. It's not definitely true with priority 1, okay? But I guess it depends on how you define the priority of measures on arms, okay? How you generate them. But in particular, if you, I mean, for dense matrices that are of reasonable size, meaning that more than 4, 5, 6 states, then this is almost always indexable. Now, if you have sparse matrices of size like 4, 5, 6, 7, then it's not, I mean, most models tend to be not indexable. So, but when you generate priority as random, and I don't know, optimization problems are probably not generated as random. So, okay, so it's not always true. It's not always true, but still, for all the models for which it is true, I mean, it gives you a nice way, okay, to define a priority policy. Okay, times is going fast.
Have extra time because of the local failure.
Yeah, sure. Yeah, probably awesome. Maybe I have too much. But yeah, okay. I want to give you an example because I think examples are nice and they help you understand what's happening. And so I go back to my scheduling examples, where here I consider that I have 2 jobs that I can run, 2 tasks that I can run. And I somehow want to minimize the completion time, meaning that if I have a task that is smaller, I want to do it before the other one. And now just let's imagine something where one task is of size 10, okay, it takes 10 hours to complete. Another one is of size 2 with priority 1/2 and 18 with priority 1/2. How do you minimize completion time? So the thing is that they have exactly the same expected duration. So you could say, yeah, expected duration is the same, so I can start by X or Y, it doesn't make a difference. But in fact, if you start by Y, there is a small probability that you will finish Y pretty soon. So maybe starting with Y is better than starting with X. Okay. And in fact, you can easily compute and define indices for this thing by using the same Lagrangian method, by just saying at the end, the intuition about this lambda is becomes like lambda will be the reward that I give you if you finish the job. Okay. And now you know that running a job for 1 hour, say, costs 1. And if you finish the job, I give you lambda. Another question is that what is the smallest lambda that you want so that you are willing to start processing the job? You can stop anytime, okay? But you are just saying, okay, I give you lambda, and yeah, what is the smallest lambda that you want me to give you? And the idea is that, okay, imagine that I have a job of size 10, okay? If I give you less than 10, you're not going to start the job, okay? Because you know that you're never going to finish the job. But if I give you 10, you are willing to process the job. Now imagine that you run the job for 5 hours, okay? And now how much, do you want me to pay you to run the job? It's 5, okay? So it's linearly decreasing from 10 to 0. So this is for my X job. And now what about my Y job? What you can show is that essentially at time 0, I should pay you 4. Because if I pay you 4, you know that if you run the job for 2 hours, with priority 1/2, it will be finished. And then you can stop, okay, working on a job, okay. But you just say, okay, I'm willing to try for 2 hours, but there is 1/2 priority that I'll get to finish the job. And so these things tells you that yes, as the intuition says, that you should run the red job first, and then if it is not finished, it will jump to this index. In that case, you should start doing the blue. Another thing that, as I told you that if you have another job, the green job, which is 3 operating 1/3 and 12 operating 2/3, you can compute the same index curve, and it tells you that the index here will be 9. And so it's again jump to 9, does something like this. And what you do here is that you start the red, it will move up here, then you start the green, it will move up here, then you move up here, and then in fact the green is still smaller than the blue. So in fact you should have the green go up to the end. So you should really, here, yeah. So treat a bit of red, then full green, and then blue. That would be your index policy. And the thing is that for these particular models where jobs never leave the system by themselves, you can prove that this is optimal, even if you have arrival of jobs. Okay. And the problem becomes, this situation is not optimal when either you have multiprocessors where you can process 2 tasks at the same time, or just when, for instance, job leave the system, and they may leave the system because maybe a task is worth 0 if someone else completes it first. Okay. But again, this was just some intuition about where index policies are. So now let me go back to this idea, okay, that we have the index policies, but how good does this thing perform? Now, so what do we have? So now Whittle index gives you priority policy. Okay, priority policy that says that I should activate first, for instance, state 1, then 2, then 3, then 4, then 5. Now, if you look at so again this macroscopic mean field view, this gives you a dynamical system, okay, where here xs is the fraction of arms that are in state S, okay, And I have a deterministic dynamical system, that is given by my priority policy. Okay. So I just write like pi whip, okay, would be my dynamical system that associated to a given state item t, my state item t plus 1. And in fact, you can show it's not really that complicated, that this system has a unique fixed point. So fixed point means that pi whip of x is equal to x. And this fixed point is the unique solution of my LP program.
Do I interpret pi WRP as a matrix?
No, sorry. So pi whip is a Whittle index policy. So this dynamical system, in fact, it's a piecewise linear system.
As with your curves in the example, do you mean that piecewise linear in time?
No. How to say? Trying to think if I can explain.
Linear in the x.
Easily, it's piecewise linear in x. Yeah.
Okay.
Yeah. So the idea is that what you do is that you I said that state 1 has priority over state 2 has priority over state 3. Okay. And now the thing is that you look at your x. Okay, x would be, for instance, I have 30% of the people in state thing, and 20% here, and 50% here. And now I have this this alpha. Okay, this alpha is the fraction of people that I can activate. For instance, it's 0.4. And what now the Whittle index policy is saying is that you activate first people that are in state 1. And if you have some remaining budget, you will activate people in state 2. And if you have some remaining budget, you activate people in state 3. And now you look at x times t plus 1. And somehow, for instance, for alpha is equal to 0.4, you will activate everyone here, and then half of the people here. And so it will give you a new vector, xt plus 1, which I don't know exactly what it is. But the idea is that just this xt plus 1 is a continuous function of this xt. And in fact, it's piecewise linear, and the pieces are really just like are when some of the coordinates sum to 0.4 and sum to alpha. Okay. And so it's related to the original system with size n in the sense that it's the expected variation of the x. Okay. Meaning that x t plus 1, the small x, no, sorry, or pi whip of big x is the expectation of x t plus 1, knowing that I start in x t. And so what has been shown essentially in the 90s, okay, is that if I said that this is this thing has a unique fixed point, but this fixed point is not necessarily an attractor. Okay, maybe there are some trajectories that jump around. But if this is an attractor, then it means that Whittle index is asymptotically optimal. And when I say if, it's almost an if and only if. In the sense that unless the rewards are really, special, so that, for instance, if the rewards doesn't depend on the state, everything is optimal. But for all given models, essentially, with the Whittle index policy is asymptotically optimal, if and only if it has a unique attractor. And in fact, what I said about this piecewise linearity is that what you can show is that if the fixed point, doesn't fall exactly on the boundary of the piecewise linear region, then the suboptimality gap is exponential. Is exponentially small in n. Okay, let me prove maybe this this result. I mean, prove relatively quickly, but again, I just say that the first idea is just to say that if I look at my state at time t+1, again, this is second state of the stochastic system. This is equal to the expectation is this pi width of xn, and then I have some stochastic nodes that comes from some central limit theorem. And now the idea is that okay, the expectation of this thing is 0, but this thing is like non-linear, so there is something to be done. But the thing that this when n goes to infinity, this goes to 0, and this is how you prove the first result that it's asymptotically optimal if you have a unique attractor. And then the other thing is that I said non-degenerate means that this thing is locally linear around this x star. And essentially, if pi width is linear, this thing is the expectation of this is 0. And so we can somehow exchange expectation and this linear function. And so the suboptimality gap is 0. And the only exponentially small thing that is left is because pi width is locally linear around x star. So you want n to be large enough so that you start close to x star. Okay. Two lines proof. Well, details are a bit more complicated, but the idea is really is really there. So this gives you like how fast do these indices become optimal, and in practice, in fact, I mean it's been shown in numerical examples that for many systems, even for n equals 2, 3, 4, the suboptimality gap is like 1%, or is really, I mean, for problem for which you can solve the optimal policy, the suboptimality gap is really small. Yeah, maybe to don't know. Trying to think of the time. I guess, yeah. One
say 10 more minutes. I mean, you were sabotaged.
Okay, if you allow me 10 more minutes, then maybe I can go for this thing. So I just want to come back on this idea of index policy, and about this idea that things are indexable when there exists a lambda, okay, such that it is optimal to activate before this lambda and not optimal to activate after this lambda. In fact, this is the definition that you find in the book. But one of the things we realized with a student, Kim Young, that Aditya knows quite well now, is that, in fact, this definition is not really that precise. In particular, if you want to have an algorithm that tests this definition, this is not a mathematical definition at all. Okay, and why it's not a mathematical definition? It's because, in fact, what is the signification of optimal policy is not really clear. Okay, in fact, when you look at Markov decision processes with average cost, in fact, there exist different notions of optimality. Gain of optimality, bias optimality, etc. And okay, it's not really fully clear what's the definition that you should put here. And the other thing is that, I mean, there are some models for which the penalty is not really unique, well-defined, in the sense that what I said is that if you look at the policy, for instance, the policy should be here is blue, okay, then there is separation, and after that it's white. But the thing is that, for instance, maybe here in this region, I don't care if I activate or not. All this region is, and in that case, what's the index? Is it this thing, or is it this one, or is it something in the middle? I don't know, it's not really clear. And so the thing is that when you want to formally test if this is satisfied, you need to precise a bit this. And so that's one of the things that we try to do, and to define some kind of a more precise definition that uses the notion of optimality that we call the Bellman optimality. And yeah, well, the idea of Bellman optimality is just that it's a policy that satisfies Bellman's equation. I don't think it has a name in the literature, this notion of Bellman optimality, but okay. We call it Bellman optimality, and what I'm just saying is that, okay, Bellman's optimality, these are Bellman's equations for time average MDP. Believe me, if you don't never seen that, you can find them in the Futterman's book, for instance. But the idea is that for time average MDP, same as you can do for a finite horizon or discounted horizon, you can define some Q value that depends on the bias. And yeah, a Bellman optimal policy is just a function that is the best response to this Q value. Okay, that computes this R max. And now, how can we use it is that if you define the active advantage would be the Q value of the action active minus the Q value of the action inactive. Essentially, our definition is just to say, okay, does this function crosses zero a unique time, or at most one time? Okay.
Can you remind me what the G star means?
What the
G star, the first.
Oh, G star. Okay, this is the average gain. Okay, so just here, lambda is just my penalty again of the thing. So if you have a regular MDP, lambda, there is no lambda. Okay. Now G star is the optimal gain of the best policy, and HI would be the bias essentially of starting in state I. Bias is high if it's a good state, bias is low if it's a bad state. And now what you have is that, for example, if you have discounted MDP, there is no G star. Okay, it's just that you put a gamma here, and this would be your value function. And the G star is just the average gain of the MDP.
J star like in a average cost.
Yeah, so for control people it's J star.
Yeah.
For MDP people it's G star. But yeah, it's the same. It's like A is U now. And so just to say, okay. At the end, what you want is that you have this function, and you want to see, okay, do these functions all across its zero axis only one? And if you do that, it's indexable. And the good thing is that because these functions are, again, piecewise linear, you can compute the slopes of everything. You can put everything together, you mix it. Again, it's piecewise linear. There is something called Sherman-Morrison formula that helps you inverting matrices when you change only one line. I don't know, really like this formula, so I put it here. But just to say, if you don't know Sherman-Morrison formula and you need to invert matrices, think about this. And then essentially, by combining all these things and doing some kind of a Streisand-like optimization, okay, you obtain an algorithm that is really efficient to compute these indices. And for instance, just to say that, okay, like if you compute indices of armed with 15,000 states, the 15,000 states, it means like, you have matrices of 15,000 by 15,000. So like 100 millions or 200 millions values. But you can still do it like in a reasonable amount of time, meaning a few minutes. Okay. I mean, maybe more than a few minutes, 600 seconds, more than a few. But it's still a reasonable amount of time. Okay. Let me just say two words about the finite horizon problem because I have my extra 10 minutes, and then I'll wrap up. And just to explain the difference between this problem and the one I had before, that before that I said that you have a unique fixed point of this Whittle index policy that corresponds to the relaxation. And so somehow the problems are sort of easy because everything depends on the fixed point, like the indices, etc. There is no time dependence. Now, if you look at finite horizon problem, you know that optimal policies, they depend on time. So if you want to say, okay, is the priority policy optimal, then you need to have a time-dependent priority policy. Okay. But still, you can write the same LP as before. And what this LP will give you is just a sequence of a trajectory, a deterministic trajectory that is optimal for the infinite horizon problem. And again, you will have the same problem as before. And I have a picture, sort of pixelized picture, sorry. But that says that, okay, now there is that what you have is that at a given time t, your optimal sequence, x star, y star, will give you, okay, x star will be the size of my boxes, okay, and now y star will be like the 8 that is here. And here just means that I activate everyone, and here I activate a fraction of this only. Another thing is that now you want to define a control policy, but the problem is that in practice, xn, you see that the size of the boxes will be different compared to the size of these boxes here. Okay. And the question is how to adjust this. And now the simple idea is just that, okay, imagine that here, what I did is that I have a state S plus, S0, S minus. And these S plus, you see, they are all full. These S minus are all empty. And these S0 are the ones that are half full. And the idea is just that if there is only one person in S0, only one state in S0, then the policy that is here is a priority policy. It means that you first fill these boxes, then this one, and then this one. If you do that, it corresponds to that. And so, and plus, you can realize that this thing is locally linear. Okay, meaning that if you change a bit one of the box, it will change linearly everything.
But could you easily explain what is S plus S0 and F minus?
Yeah, so the idea is that you look at X, you look at the XS, and you look at when XS is equal to YS1, you call that, this means that S is an S plus. When XS is equal to YS0, it means that you don't activate, you don't choose to activate action here. It means that S is an S minus. And the rest is S0. So S0 are the ones for which you have essentially both Sx0 is positive and Xs1 is positive. And so, yeah, the idea is that just if you have exactly one person, one state in the middle, this becomes a priority, or this can be implemented as a priority policy. And so what can be shown is that essentially there exists a priority rule that is asymptotically optimal if and only if the S0 are all smaller than 1. Essentially, it's the only way you can. Of course, there are some. I mean, you can order S plus as you want. Okay, but there are many priority policies. But still, yeah, you need S0 to be smaller than 1 to have a asymptotic priority policy that is asymptotically optimal. And the convergence rate is exponentially fast, and the arguments are exactly the same as before, up to the technical details. I wanted to give an example, but probably I won't. I wanted to come back to this applicant screening example. But just to say that, in fact, so there is, direct constraining can be implemented at this finite horizon problem. And here, in fact, you can see, we can talk later if you see it, but typically this is an example where there is no priority policy that is asymptotically optimal. And you can still construct policies that are asymptotically optimal, but they are not exponential, they are not fast. The suboptimality gap is not exponentially small now. Okay, it's in square root of n, and you can really, you can't really help it here. Okay, let me just wrap up what I've said. So today I talk about essentially Markovian bandit and restless Markovian bandit in particular, for which I presented this relaxation that looks a bit like mean field control relaxation, and that is nice for these problems because everything is linear, so everything can be solved by an LP, so pretty efficiently. And again, this relaxed problem, you can define exactly the same thing for weakly coupled MDPs, where the action space is a bit more complicated. Okay, because just you have a linear constraint, you do the same linear constraint. Now, of course, not everything will translate exactly as I did. Okay, and the thing is that what I presented was to say, okay, now we have priority rules. There are many cases that are asymptotically optimal, and in general, when they are asymptotically optimal, they become asymptotically optimal at exponential rate. And think that it's good. And when they are not asymptotically optimal, that means they are not asymptotically optimal. And most of the time they are good heuristics, but anyway. Now these results like this, they do not translate directly to weakly coupled MDPs. For instance, index policies, when you have multiple constraints, this is not clear exactly what it means. Okay. Or similarly, priority rule, if you have multiple constraints, it's the same. It's not really well defined. Okay. So yeah, there is a bit more of questions notation. Some of the results translate to weakly coupled MDP, not all. What really translates directly is the relaxed problem is exactly similar, but the way to go from the n infinity to finite n is a bit trickier. Yes, there are different questions that we can think of. Here I'm mostly focused about going from the relaxed problem to the finite problem for finite state space, and how to compute this, how to make it efficient. Now, of course, if you go to some continuous state space, things becomes a bit more tricky. Okay. For instance, because computation, clearly the algorithm that I gave for computing, doesn't work for continuous state space at all. So there are probably some interesting questions for that. Okay, and the slides are available online, so do not hesitate to reach it, look at them if you want. And I'm still here today and tomorrow. I'm still around, so don't hesitate to talk to me.